Welcome back, and this is lecture number 6, which is the continuation of lecture 5 regarding MATLAB demonstration. So, in this lecture, since we have already implemented a series RLC circuit, now here we want to implement a parallel RLC circuit with parasitic. That means, we are considering the inductor DCR as well as the ESR of the capacitor. And we already know from our lecture number 4 that this building block diagram was actually realized from this parallel RLC circuit. And now, the steps are common in order to build the block, the procedure. That means, we have to select the parameter symbol and we have to put those symbols into the .m file, script file. We have to also assign some values to these parameters, and the same parameter should be used in the Simulink block. Okay. So, this file for this particular case study, we have considered inductor to be 2 microhenry, capacitor to be 100 microfarad, resistance as 0.5 ohm, then RL the DCR is 10 milliohm, then RC 5 milliohm, then inductor initial value is 0 ampere and capacitor initial value is 0 volt. And all this will be saved in a separate file .m file, which is now named as parallel RLC parameter.m. So, let us go back to the MATLAB simulation block. In this MATLAB simulation, okay, what we want is that our this file, that means parallel parameter parallel blocks. These I have explained. Now, we want to build this parallel RLC circuit. And we already have the equations. Which equations are there? These equations are our these particular blocks. This block need to plug in. Now, what is our next task? So, we need to go for Simulink block, and we already know the different blocks needed from the library, which are needed to realize this particular parallel RLC circuit. So, this integrator corresponds to IL initial value, we will call it as IL 0, and we also want to use another for the capacitor, which is say Vc 0 block. And now, we have this initial values which are here. This initial value we will store it here, initial value, and the other one we have this block that we want to store as an initial value for the capacitor. Okay. Next, we know the right side of this block will be inductor and left side is the derivative. Now, we want to use another gain block, which will be used as a 1 by L in block, 1 by L block, and for the other one we need to put 1 by C block, 1 by C. So, now we have one side we have one side we have the left side we have capacitor current and the right side we have. So, this side is capacitor current, this side is inductor voltage, and this side is inductor current and this side is capacitor voltage. Okay. Now, what is our next task? What is the inductor voltage VL? So, VL, if you look at VL for this particular example, VL is V in minus ILRL minus V 0. Okay. That means now we need to connect this summing block and this summing block. So, this summing blocks, and here we need 2 subtraction, 1 addition. So, the first subtraction will be the ILRL drop. Okay. So, that means we need another block another block here, just a minute. Yeah, we need another block. So, this block is RL. It must be consistent with our this RL and RC. Okay. So, this must be consistent, RL block, and this is subtracted, and this will be the first term. Okay. What is the second term? The second term is V in, which we will also set like a another constant. So, we can call it as a constant. We can set whatever V in we want. So, this is our V in. Maybe we can just give a constant value. Okay. If we want to choose a separate V in, it is fine. Earlier example, we took a what we took a source, from the source, and we take a pulse generator. Okay. So, we will continue with this pulse generator, and we call it as a V in, and we will use the same pulse generator where the time period was 1 millisecond, and the value changes from 10 volt to 0 volt with 50% duty ratio. That is it. Now, the other subtracted block from the parallel RLC circuit, if we refer to this circuit block, if we go back. So, this is V 0, this subtraction block is V 0. So, but we need to generate this block, this signal, and this is generated from here. So, the capacitor voltage, the capacitor current is inductor current minus load current, and load current is derived from output voltage by R, and output voltage is derived as the capacitor voltage plus the capacitor current into RC. Okay. So, with this, let us move to this MATLAB Simulink block. Okay. Now, we can consider a block here. In this block, we need capacitor current, inductor current minus load current, and inductor current here we can simply connect here. We can simply connect here, and this block I can raise a little bit. We can simply connect here. Okay. We need to connect. So, this current is the capacitor current. Now, if we want to generate the output voltage, what is output voltage? It is a combination of it is a combination of capacitor voltage, which is here straight away connected, and the other combination we need to put RC, which is RC capacitor, RC, and this is my capacitor current, and this I will simply connect here, and this is my output voltage. Now, so what is my load current? So, my load current is here. So, it is 1 by R, that means voltage by resistance. So, this is output voltage divided by resistance. So, that is my load current. Got it? And now, we have the output voltage. So, I can simply connect it from this block, and now this all about our, now our model is ready, parallel RLC circuit. That means everything I have included. Now, we need to check the signal, that means sync. We need an oscilloscope. Here it is a scope. What do you want to display? Here again, in the previous presentation I told the scope, we can set it like a 3 channel, and we can history term, we do not want to, we need to make like a result, and it should be structured with time. Now, we have generated 3 scope. So, this scope is actually the first channel indicate the inductor current. The second channel we want to show the output voltage, which is this voltage. Even we can see the capacitor voltage. So, whatever we want, and the third one we want to see the capacitor voltage, let us say, for the time being. Let us see what happened when it simulated. So, you can see that for this time instant, for this parameter value, so the top waveform is showing the inductor current, output voltage and the capacitor voltage. Is there any difference between output voltage and capacitor voltage? Because there is a capacitor current multiplied by resistance. So, some slight difference will be there, okay. But I want to see the input voltage profile, how does it respond to the input voltage. So, I will connect to the input voltage, and like the previous case study, once we simulate, it is not necessary that we need to see the result from the directly the Simulink scope. We want to see the result using the MATLAB figure file. So, again we can use the same V in V0 IL we have connected consistently, and we can use this plot command and plot it. So, this is what it is shown, and again we can put connect all the axes, like if we select this channel, we can insert x level as the time in second, then we can y level, so which is my output voltage in volt, and this channel if we select, then we can add inductor current, and since they have the same time axis. So, it is not necessary that you need to put, but if you want you can also set the x level for this also, time is second. Now, you can go to export setup, where we can set the font size bigger, and we should use Times New Roman, and line size you can increase to 3 if you want, yes, and it will show like this. If you want to change the color of this scope, you can select the color, say you want to use a blue color, you can use it, that you go. So, this shows that how to simulate inductor current and output voltage from that. Which block we are talking about? We are talking about this block, parallel, and this kind of result you can see from the scope. So, this is a parallel RLC circuit implementation using MATLAB. Now, we need to do like a modular block. That means, let us go back, and we know that how to create the subsystem block, right. So, what we will do? We will keep those outside, and this whole block we will select, and we create a subsystem. So, we have to first select this block and make subsystem, create subsystem. Once we create subsystem, then we need to write like a parallel RLC block, parallel RLC block. Okay. Now, we go inside. What is the input in this parallel RLC block? So, we have to specify the inputs and output. That means, let us write down, I think. Okay. So, the first block here, what was there? It was our input, sorry. So, this was our input voltage V in, and the second block output we want to see So, we want as many number output we want. This is my inductor current IL, and the third block is my output voltage, not the capacitor voltage. I can write V0, and if we want to place another block, another output which is an optional, because I want to check the capacitor voltage also. So, I can create another channel and just plug it and go back, and you will see now my parallel RLC circuit building block is completed. Now, this building block is much more easy to simulate. Okay, this is a scope. So, whatever we did earlier, it will remain same. We can run it, and then we can repeat this we can repeat this waveform, and it will show the same results. That means, what we learn? We learn how to build simulating block from our block diagram representation, mathematical which was derived from mathematical model, and we have created subsystem, and that subsystem we can call it in my subsequent blocks. Okay. Now, our next task. What is our next task? So, next task is to implement a conventional buck converter. So, now it is a complete diagram. If we look at the parallel RLC circuit, if we take that, this part is common, this part is common, but this part is common. So, we can use that parallel RLC branch without any hesitation, we can use it. But we have to be careful about the selection of that inductor voltage, which is a very crucial, because we know that inductor voltage, if we want to enable the discontinuous conduction mode of operation. In fact, instead of starting with conventional buck, let us start with the synchronous buck, that will be much more easy. So, the synchronous buck, we have again implemented this block. Okay. So, here only difference is where is the difference? This block we have already made, that means this block we have already made in our Simulink is a parallel RLC branch. This block is also we made in the parallel RLC branch, like this branch. So, if we look at this diagram compared to parallel RLC branch and this circuit, what is the difference? It is a Vx. That means, if we retain the parallel RLC branch and if we incorporate this Vx, then our job is done. That means, if we go back in this block, we want to replace this V in with Vx. That means, that is a switching voltage, switch node voltage. So, our job will be done using this block. So, then what is our next task? Okay, let us go back and we want to build this model. Now, we want to develop now synchronous buck converter. So, let us save as a synchronous buck. Now, I want to show you that these blocks are much flexible, and I also want to show you the synchronous buck. I want to also set the parameter value. That means, let us say whatever parameter of the RLC we have chosen, we will save as another file is a synchronous buck, and this is my parameter file, parameter. File. Okay. So, in this parameter file, we are keeping the same L, C, R load resistance, everything similar value. Let us say we can change this value, there is no problem. Now, let us go back. So, in the synchronous buck, what is now input? So, this we call it as a Vx, the other branches are common. So, we can use this block, this is common, and this block we need to create. This block is not very straightforward because it has to come from a switching block. So, let us disconnect for the time being. So, we already have a parallel RLC branch. Now, we have to create a block. So, how do you make this block? If we again go back. So, here this is the block I am talking about. I need to implement this block now. So, this block consists of Vx, which, so I need to define two additional parameter R1, R2, which are the R1 is the on resistance of the high side switch, R2 is the on resistance of the low side switch, and this Vx will be generated using a switch block. When the switch is on, then if you look at this Vx terminal, the Vx will be V in minus R1 IL when the switch is on, and that is when my Q is equal to 1, right, and it will be minus R2 IL when Q is 0. So, this switch block we have to use. Okay. So, let us go back to this block, and if we look for switch, we should search for a switch block. Switch should be available in the Simulink. Let us wait for a switch block, discontinuous block, and in fact, we do not need to look for, we just have to cancel. The switch block should be, because it is a general purpose Simulink block. So, we can use switch block from here. Okay. Okay, I think it was about to come. In fact, we can use a function block, MATLAB function. Either we can use switch or you can use a function block, that may be better. So, whatever we want, because now the simulation is a bit slow here. So, our only purpose is when the Q is on 1, it will take this block, the switch block, so I think it is getting, so you got switch block, that is it. So, this switch block we have connected here. Okay. Next, we got switch block. So, as I said, we have to put a threshold value of the switch. Let us put 0.5. That means, if my this input is, just a minute, if the input to the middle channel, which is the input, let us say I set a if this input is greater than 0.5, then it will take channel 1. If it is less than 0.5, then it will take channel 2. Okay. So, we will select some basic blocks and we will select some of this block. Let us take, we need some of this block just for, okay. So, what we need for the first block, that means when the switch is on, Okay, it will take V in minus R1. So, I need only 2 block. Okay. Okay, I need V in. Okay, sorry, 1 minute. So, this is my first block where I have to define what is the on resistance. So, this is coming from inductor, we can simply connect it like this, and this is my R1 R underscore 1, that is my on time resistance of the high side MOSFET. Okay. And this is now my new V in. Okay. And then when this is off, it is simply a minus sign, sorry, another gain block will be, this will be what? It will be equal to I n minus R 2 for this channel. Okay, got it. Now, input channel will create separately, and we will create another channel, let us say so sources. So, commonly used block we can use a constant, and that will use as a constant. So, that will use as an input voltage, because input we need a DC voltage, and we can use a switch block here, that is for my generating the gate signal, and that we go. So, yeah. So, now we have all sort of blocks which are coming out. We need to see the output voltage, we need to see the capacitor voltage. So, this block now we can create a subsystem calling as a, so we are creating a subsystem, this particular block create subsystem, and this we call as a synchronous buck. Okay, and we actually expand. Okay. So, what are the blocks? The first one, this in is a V in. So, this is V in, and this is my gate signal, which is my gate signal. Okay. And these are my output, this is my inductor current, this is my V out, and this is my V c. All right. So, we got input voltage V c. Now, we can set input. So, here we can choose a V in voltage that you want to select, which is my V in. Okay, V in is already there. So, input, we can say input, and this is my gate pulse. Okay. Now, suppose if I set a gate pulse time period t that I am going to set, and with let us say 50% and amplitude 1, because gate signal will either high or low, logic 0 and logic 1. Now, we have to define all these parameter inside my this file. So, what is missing here? Here is missing term is R1, let us say, which is maybe 5 milliohm E minus 3, R2 which is let us say maybe 4 milliohm you can customize what you want. And other parameter V in, let us say we set 12 volt, and initial voltage we have set 0 and 0. Okay. So, now I hope we are ready to go for simulation, and let us see. But okay, close all. So, what is missing? If we run, it will give error because okay, time period is not set. Time period is not set, but how is it taking the time period? T. Okay. So, somewhere the T is there. Where is the T? Undefined. So, we need to provide T which is equal to 1 e minus 6, because that is my Now, let us go and simulate. So, we can see that output voltage, these are my inductor current for the given inductance value, and this is my output voltage, and this is my capacitor voltage. These are my. So, what I can plot it here, that means now in the go to the waveform, I think I have used this result block. We need to check that name is fine. Now, we will go for this one. So, first channel was VL, V0, and this is my VC. So, VC. Okay, all right. So, again we will do subplot. Now, in this subplot 2, that means we have to plot output voltage and capacitor voltage also. I want to show you how the capacitor voltage looks like. Now, what is the difference between these two using a blue color, and we can do hold on. Okay. Now, we will simply run it. Yes. So, if we run it, inductor current is showing like this, output voltage is shown like this, and if we look at closely look at this waveform, that means if we closely see around this time frame, let us say we choose like in between 3.8 to 3.9 microsecond. So, 3.8 to 3.9 microsecond, if we choose this window. Okay. So, in between 3.8 and 3.9, 3.75. So, I can choose this 3.9 to 3.8 like this, and here also I can choose 3.8 to 3.9, 3.8 to. So, these are my waveform, where the blue one is the capacitor voltage and the red one is the output voltage. So, due to the ESR, the output voltage and the capacitor voltage are not identical. So, there is a slight difference in this waveform that is visible. Now, so we are able to implement this buck converter, and I will leave it to for the next session. I will present that how to incorporate the DCM enable operation. How to incorporate DCM enable operation, I will make that presentation in the next one, where I want to implement when we want to consider discontinuous conduction mode. There we want to show that, because right now we are only running the synchronous buck converter, where we do not care about the discontinuous conduction mode. It will always operate in continuous conduction mode. But if you want to incorporate DCM, then we need to add an additional block where the zero current detection will happen. Because if you look at this waveform, the inductor current actually is also going to the negative direction. If you go to this waveform, if you plot it, you will see at some point of the time the inductor current is going in the negative direction, and which is not possible when there is a diode. So, here it is fine, this is fine. Okay. So, I think that is all for today. So, we have learned about how to implement a switching converter, and that we have derived based on, if you go inside the synchronous buck converter, it is a parallel RLC circuit, and there we just added this switch block, and that implement our synchronous buck. A same model, if we add some more feature, it will become conventional buck. In fact, we can also slightly modify this block to create a boost converter. So, all this model will be shown at this point, but here I want to show from future onward, we want to show the building block directly rather than developing from the scratch, because last two presentation, this one and the previous, was aimed to show that we can develop custom building block using MATLAB Simulink. Thank you very much.